Good morning, good afternoon, or good evening. In this workshop, we are going to talk about common security bugs related to Unicode and some of the complexity of handling Unicode within our program. I will start with an incident, following with common bugs which related to the Unicode, and I will conclude this workshop with a lab. You can follow along the lab as I am doing it by heading to learn.secteam.com. So with that, let's get started. In 2013, a security bug was reported to Spotify that allowed a user to elevate its privileges to any other user account. So in other sense, a user could become any other user, impersonate any other user, even high privilege user account such as admin, root, so forth. Obviously, at the time of doing this workshop, this bug has been addressed by Spotify, and also there was a blog post written about this issue. So what went wrong? Let's look at the attack scenario. Step 1. Register a new user account with username. Suppose we want to register a user account such as Big Bird, but we are not going to use the ASCII characters to register this. As you can see, these letters are slightly different. Although they look like in a capital form, we are using a combination of different characters here. Once you register that user, request for a password reset, then follow along and do a password reset on that user account, and later on follow along the email link that was sent to you, and you will end up resetting someone else's user account or the real Big Bird. Now the incident is quite interesting because it goes back to the complexity of dealing with Unicode characters. What was the root cause? Well, I can simplify the root cause in two areas. One, the ability to register a username with Unicode characters, and the other thing, usage of an unsafe normalizer, or put it Unicode normalizer, to filter Unicode characters. To fully understand what actually went wrong, we need to understand some backgrounds and fundamentals here. So let's use a time machine and travel in time and go to 1979, when there was the days of floppy disks, soft 5-inch disks, green and dark terminals of the Unix systems. It is a time that we want to obviously display some characters on those green and dark screens. Our systems, although accustomed to show us 0 and 1s, because those things doesn't really make sense to us. So we were looking for a way to transform those bits of 0 and 1, the stream of 0 and 1s, to something which is more human friendly. Well, the algorithm that we use to transform those bytes or bits to characters is known as encoding. And at this time, there was American Standard for Information Interchange, most commonly known as ASCII, was proposed. And thankfully, it was used across a large number of systems. If you head to your terminal on OS X or Linux, if you just type man ASCII, you will be prompted with a table such as following. And we will see that how in ASCII standard, every character, such as A or B, has what numerical value, which behind the scene, this numerical value will be converted to binary, those 0 and 1s. And one thing we should keep in mind here is that ASCII only uses 7 bits out of 8 bits that is available to encode English characters and some control characters. And let's keep in mind these control characters because we will see what's going to happen to them. Now, if you are asking what are those control characters? Well, I have included some of them here. look at, for example, the character bell, which is a hex of 0.7. What does this character do? You may have guessed. Well, it just creates a bell sound from the computer speaker. Or characters such as 0 and 0, some of you may have been familiar with the notorious null character. Let's travel into the time again, and this time go to around 1990s, where we want to find a way to encode other languages, not just English, in our computing systems. And what happened was that those 7 bits in ASCII was no way enough to encode all characters across different languages that we wanted to support. The other thing was ASCII used only only proposed 127 characters, including some controlled characters, and there were some remaining bits in that standard that could be reused potentially to encode all other characters that we were interested. So what happened here was that the game started and there was a lot of companies and organizations that started to proposing what mapping algorithm or what binary should be mapped to what character. And what was the result? A mess. There was around 465 different encoding was proposed. We called them code pages. And some of you may have remembered in the early days of web, you browse to a website and what you see is such as a screenshot you see here, a garbage text. This problem was so big that it got its own name, Homogeleif. And it was because the display system or the display software was using an incorrect encoding or code page. So what happened then? We needed a way to come up with a consensus. We can't just deal with this inconsistency across code pages. As you can imagine, there we go. Unicode came around to save us, which is known as an international encoding standard that for every number, digit, letter, digit, and symbol, we have a unique number. And it also consistent across different platforms, programs. We can think about Unicode as a hyper collection of lots of code pages. It covers most languages. I don't want to use the word all because there are some languages still not in Unicode, and it has a lot of space to grow. There is a lot of space within Unicode standard that are intentionally left empty for potential future extension. Now, in Unicode, suppose we want to represent this phrase, hello, space, dog dirt. For every character, there is an identifier starting with U plus, following with a hexadecimal number. Why hexadecimal number? Because hex was more compact way of representing that code or that identifier. We could use any other number in here. So just remember this is hex. And these identifiers in Unicode standard is called code points. So anytime you hear code points, that's what we are referring to. And also what we have a description for that code point. Like for example here, character H is 0048. It's a Latin capital letter H. All the way down, character space is 0020. And finally, the pile of poo, dog dirt also has a code point. At the time, there was some other competing standards of Unicode, but Unicode was also backward compatible because that was the key with ASCII. We don't want to throw out all those Unix systems. Happy days, things seems to working very well. Before I move on, let's not confuse these code points with things like UTF-8, UTF-16, UTF-32. Those are different things. Those are that I'm not going to cover as part of this workshop. So I'm not talking about that these code points uses 1, 2, 3, 4 bytes. This is not the story here. We're just talking about every character has an identifier. Some of the characters are using 4, let's say 4 digits here. Some may use more. I'm not referring to anything related to UTF here. New problems started to emerge. As you can imagine, we have this huge, let's say, standard that encompasses many languages. And as such, we have some similarity between some characters due to some reason. Up until today, well, if we look at some of these modern user interfaces, this is a screenshot that I took from one of these systems. There is no way for us to differentiate, or me as a user to differentiate, which one of these email addresses are actually valid. Or should these two email addresses be treated the same because they look the same to me? But in reality, these two email addresses that you can see here are not the same, because you can see that there are two of them being represented here. So this is just one example of that it's hard to differentiate. Let me give you a more interesting example. Now, you don't need to be JavaScript dev to understand this very trivial JavaScript code. My question here is that what will be printed out at this line when I make a call to attack a strategy function? As you can see, I have this function defined multiple times, each time returning a different value. Would you say it will print out attack at dawn, or attack at dusk, or again attack at dawn? Maybe a better way for us is to actually run it. I have an online repo for JavaScript, and you can see I'm using the Node version 12 here, and this is effectively the copy of that code that I had in the slide. So what do you think? Let me run it. Attack at dusk. So what is going on? I can clearly see this function attack strategy was overwritten here, but still this seems to be this function referring to this function in middle. Well, this to do with one of the problems of these Unicode, or things that we may overlook or miss. We have a concept called Homogeleif, or simply confusable. This is to do with simply three areas. We have a font that does not clearly distinguish between these similar characters. The most notorious example is 0 and O. Or combination of multiple characters that look similar. Very simple example is RN and M. And finally, where Unicode contributed the most is some characters in a single or different script. And a script in the context of Unicode means language. So we may have a letter A in Latin or letter A in Cyrillic. Both look exactly the same, but they do have two different code points. And two different code points means that the computer system will understand it differently. It will treat it differently. Was that all the problems? Unfortunately not. Let's look at another issue. Well, this time I make an example of a Python code, a trivial Python code, that we have a global variable called balance with 1,000 value, and I have a very basic function called withdraw that it receive an integer value called amount. Then it will deduct that amount from balance and return. So the state of this variable will change when this function calls. Now, if I go ahead and call withdraw twice with 500, what will be printed out at this line? Would you say 0? Or would you say 500? The program will crash. It will not run. Interpreter error. Let's look at it again in a REPL, an online REPL here. I effectively copy and paste this code from here to this REPL so we can see what will be the result. And as you can see, I just run it. And surprisingly, what we are getting here is 1000. And if you want to say there's a problem on this line, actually there's no problem on that line. There are just some linting issues related to the fact that I'm using a global variable here and I have not used this, well, this linter thing that I have defined a local variable and I haven't used it. So the issue is not there. This seemingly benign code, it does not do the thing that we were expecting. So what we are seeing is not what the interpreter knows, understands, and unfortunately applies. So what is the problem? If you remember, I mentioned twice about these control characters, and Unicode has quite a few of these control characters, one of them being BD or bi-directional characters. These are the characters that are invisible, but they will change the logic of the characters that they come after them. They will make the system, that display system, to treat the characters that comes after them differently, or the series of the characters that comes after them differently. Why do we have in them Unicode is because, for example, we want to support languages that are written from right to left. There are quite a few of them. I have selected a few of them here. For example, code point 22b is a right to left embedding. We have code point 22d, left to right override. And I'm not gonna go through the details of all of them at this stage, but just let's think about them. There are some of these invisible characters here that will make the code to, well, the display to render something very differently from what the computer can understand. So if you are curious at what actually happened here, there is one of those BD character used on this code. Now maybe if I highlight this line, you may notice it here, that this BD character has came right after then. It make whatever comes after it in right to left. So effectively, this code is what the interpreter will see is actually this. Withdraw. I put the space at the beginning, font, and then closing the comment, return. So our withdraw function doesn't do anything, it just returns. And that's why we got this value out. So are we done yet? Do we have any other issues? Well, unfortunately, we still have some issues with the way that we need to treat Unicode. True or false? I'm just doing a lens on the character dog dirt. In my eye, it's a single character, so the lens should be 1. The answer is, it depends. Python and Swift, these are just a few examples I've picked here. They will consider as lens 1. JavaScript and Kotlin, they will give you lens of 2. But there is clearly what I call it as a lens differential issue here. But is that all? Well, not really. I want to now give an award to a highest, well, and the award is called the highest lens award. and that will goes to Go, which will gives us 4 when you do a len on this Unicode character. So it looks like a mess, but it's not as bad. The situation with these complexity or these edge cases with Unicode. Let me simplify these things to a few categories for you. So when it comes to Unicode security issues, or let's say edge cases, we can classify them into 2 groups. Things that you as a software engineer can do something about them, and things that we're relying on our users to make a safe decision. And I will go through all of them a bit later. So one thing to remember is that the things that why we need to care about this, well, we saw one incident right at the beginning of this workshop that Unicode can cause account takeover. That was a real incident of that. But commonly, these characters could result into security validation bypass. And imagine in the current heterogeneous environments that we have multiple services that are passing the data around, and we may use different languages to interpret these values these values that are passed around, and those values could come from untrusted source. This could result in the things that being interpreted in one of those services, say maybe we have a Node program or a Python program that sits in front of a service that written in Go, and as you can see, the length of a character is not interpreted the same between Python code or Go code, and this is like opening can of worm that a lot of other issues can arise in. Obviously, if one of those languages are not memory safe, we're gonna go to all the problem of buffer overflow and related security issues. And finally, as you could see in some of the code snippets that I've showed, these could result into a number of spoofing attacks as well. It could be related to our end user or even software engineers. So let me start with the things that we can do something about them as a software engineer. Well, a string matching, or I call it a string mismatching issues. Now, if we have 2 phrases, like let's say this is something in our system we want to check against, this is something that comes from an untrusted source, how do we make sure that these strings are equivalent or should be treated as equivalent? Or are we comparing apples with bananas? Maybe the second string may contain some Unicode characters that might be interpreted differently. To really understand this, first I should talk about what equivalency means in Unicode. We have 2 types of equivalency. One is canonical, the other one is compatible. Now, canonical, we are saying that in a canonical way of equivalency, we have a same abstract character but must be treated the same. So canonical is like a strong way of comparing 2 things. Now, compatible, on the other hand, it talks about we have a similar abstract character, but it can be interpreted and treated differently. Now, compatibility is more like a weak way of comparing 2 things. Now, in a string matching, if you want to be 100% sure that what you are comparing apples with apples, you want to opt for canonical equivalency. You may ask, how can I drive a canonical equivalency? Well, that will bring in the next topic, which is known as normalization. Now let's think about a normalization as a way for us to drive one of those equivalencies. There's a function or algorithm that we run our input through, and as a result, we get one of those equivalency. In Unicode standard, we have 4 types of normalization: NFT, NFC, NFKD, and NFKC. NFT is canonical decomposition. And what does decomposition means? Let me whiteboard this for you. For example, if we have a letters A with an accent on top, decomposition means that we decompose this character to A plus another character which talks about that accent. Now, let me go back to the slide. We have another term called canonical composition, which is all about you combining these characters that composes this letter A. Now, I'm simplifying a lot of things here behind the scene when it comes to the normalization of any of these forms. There is a lot going on. But what we want to take from here is that anytime you are doing a normalization form or the algorithm or a method that you are using that behind the scene does NFKD or NFKC, we should remember that what it does a compatibility decomposition. So the character that it will decompose to is not necessarily the same abstract character. It's a similar one. And similarly, NFKC is a compatibility decomposition. So first decompose in this normalization, decompose those characters, then merge them together to a canonical composition. Let me give you an example so these things make more sense. So again, NFKD, compatible decomposition, and NFC, so canonical decomposition followed by canonical composition. So in this form, we only perform canonical equivalency. In these forms, we are doing compatibility composition with the exception of the last one. So I've just picked this one and this one from here. If you perform NFKD on, I don't know, 1 inside the circle, well, it's gonna give you 1 because it's the most similar looking character to this. However, if we run NFC over the same character, we're gonna get the same character back because although it looks the same, it's not the same abstract character. For things like 2, say, power 5, in NFKD transformation or normalization, we're gonna get 2 and 5 as like a 2 separate digit. When you apply NFC on it, you're gonna get 2, but the superscript 5. Because 2 is the same abstract character, but 5 is not the same abstract character for the same for the superscript 5. So why that this matter is that this we don't want that when before our string matching these characters suddenly change to something else. Like maybe user enter this, but what we want to match is this. Or what we are end up matching is this, or user enter 2 power 5, but what we are matching is 2 and 5. So as you can see, things like NFKD will result in this sort of situation. So if you take a base here, if you are dealing with identifiers, and by identifiers I mean things like username, user account IDs, email addresses, our safest bet is to eliminate Unicode 100%. That means that in those cases, we need to restrict the character set to ASCII, or better sense, to safe ASCII range. We do not want to allow users to have emojis in their identifiers. This is also the most recommended way by Unicode standard. And here you can see I highlighted the fact that we need to limit it to the safe ASCII range because, as you remember, there are some control characters in ASCII also. Null, I don't know, the bigger than a smaller than sign, a bell sign, which does not make any sense if you use it or if you allow users to use it as their identifier. So you want to get rid of them. I've actually seen quite a few codes that they think they have limited to ASCII, but they do allow those control characters, which could result into still problems. And one thing that perhaps we overlook a lot is to case fold it. Like, say you have a registration system for an online forum or a discussion board. Now you don't want to allow users to register user admin or root, all a small case, but what one person register admin all in capital case or root all capital case or different combination of that. So if you want to do a safe string matching for identifier, do not allow Unicodes. That's the safest bet. Restrict the ASCII to the safe range and case folded. Just after this, perform your string matching. Now, some of you may already say, but wait, we want to allow emojis in our Unicode or in our identifier, or we want to allow Unicode. How do we deal with those situations? Now, I want to talk about the situation that you're not using identifiers, but let's say you are dealing with a comment or a post or something that users they can do. In those cases, you need to make sure that you have performed normalization before your string matching. And the safest normalization to use is called NFC. So remember your mobile phone, there's a thing called NFC in it. That's pretty much the algorithm that you want to use before doing any string matching. Otherwise, we may get into the situation that we're comparing two different things. We may have let's say a blacklist for word big bird, but if user comes in and enters something like that. The other sets of issues that it comes to Unicode are the things that we need to get user to make a safe decision. These category of issues are referred to as a visual spoofing, and we have seen examples of that, the user interface that I show from that email web client, and also the code that I'll show you from JavaScript or Python that was loaded into an IDE. In those situations, we can't really decide in our code that what is the intention of the user. Does the user really wants to send an email to that email account that look like security but may have a one character different? But we need to warn user about those situations. And this is one of those areas that I commonly see that is completely neglected. And as those examples, that there is no way for user to differentiate that what they are actually dealing with is a lookalike. So what we want to do, we want to arm our users with a guide. We need to detect those homogeleif, confusable, and BD characters, and we want to warn users that, hey, there is some variations in the things that you see. The things that you see is not what you may really want to. I've taken a screenshot from GitHub that, for example, if a code base that you see or a code example you see on GitHub, if it contains one of those BD Unicode characters, you're gonna see a warning like that, following with a warning on the line that that issue actually happens. And this is a really nice way to let the user know about this problem and let the user to make their own informed decision, because there could be a user that maybe wanted to use that BD character inside their code, but at least they know about it. Perfect. So what I'm gonna do from here is I'm gonna move to our lab and just see example of some of those things in a sample lab, just some of the things that we have explored together. Now for the lab, you can head to learn.secting.com and you can pick any of these languages that you see here. All these labs are open, and you just need to create a user account and get access to them. And if you hit on, in this workshop, I'm going to just go through the one in Python. If you hit on Python and scroll down to Spotify Big Bird, and you can go straight to the lab itself. If you want to listen to what I have already covered, you can find it in the introduction part. Go there and make sure you are logged in and you press on download. This will give you a URL that you can clone. Let me move to my terminal. Pop this URL here, already cloned, and move to that directory. Now, one warning here, these labs contain vulnerable programs, so please do not run them in your production system, and anytime you finish using them, just get rid of them or run them in a more safe environment. They're not prod safe. So in each lab you can follow, there is a lab guide that you can refer to it on a website, or there is also in this repository. You can run make build command to build this lab, the Docker image that accompany this lab. I've already built this before, so you can see it went super quick. So everything is built there. Then you can run make test. Make test will execute usability test, a common unit test, integration test, just to make sure the program inside the lab does the thing that it should. That one was also quick. This is a prompt normally you want to look for. And it also comes with the sets of security unit tests, or we refer to them as them example-based security tests, which test some of the potential security problem within this lab. And it's a way for us to guide if this program is still vulnerable. Now, typically these security tests are incomplete, but at least it will point you toward the right direction, which part of the code may have security issue. Now, as we can see here, that there are a number of tests are failing. And if you look closely to the title of each test, you may have some idea that what is failing. All right. So our goal in each lab are twofold. One is that we need to complete the security test. So where are those security tests? If you head to the source directory program, in this example, there is a thing called test security.py. In the labs in the other languages, it's a similar trend, but it just could be in a different directory. This will give you the security test that was tested against program. And as you can already spot here, this security test, I'm using PyTest, for example, in here. And I am giving the program a string such as that. Some of them you can see are not even represented in my terminal-based Vim. And there is obviously an assertion here that expect that given this character, I want to receive true, however, I received false, things like that. And you can also see an example of this. So why this test is failing, if we look at the program code, this is a Django program. So we have a view which has two routes. One is index, the other one is register. So this is where the program is. I actually forgot to show you how you run this program. If you just hit make run, this will spin up the program. And this tells me that there is a server running at this port. So let's move back to our browser and head to this IP address, 8080. And it's a really basic program, just tells me that, hey, you need to view this page. So I can do that. And so effectively it takes the parameter called username, a query parameter, and it will check if this username is safe for registration. So I give it Alice, you can give it different values. Now, what are the other values you can try? Well, I've given a few of them here for you. Obviously, you want to try some Unicode characters, some emojis, and to see if this is an identifier. Obviously, these things should not be allowed. So that's a problem there. Let's go back to the terminal, review the code as well. We reviewed the view, and here we can see, if we look at some of the imports, we can see we are importing from these utils. Let's look at that. because whatever request that comes in, it will look inside the GET request, take out the username query parameter, and then it will take it through this utility function, has bad character. If it has a bad character, it will respond with error. Otherwise, it will respond that username is safe for registration. So that's how, and the way that it represents that is using another function to represent it. All right, let's quit that. Let's look at that utility function. Very trivial and basic. It effectively, the bad character is only effectively care for a single smaller than sign, which kind of gives us some idea. Maybe the only thing it tries to avoid is cross-site scripting, because it doesn't like to see that character inside the username, because later on it will display the username to the user, and that's pretty much it. And the render function, perhaps something comes to your mind now, is it does use a normalizer, but it seems like not to use the safest one. All right. So our goal effectively from here is that firstly, we need to go to effectively the same file or any part of the program and address this issue. So we are dealing with an identifier. We need to make sure that identifier does not allow any Unicode characters, and also it only allows a safe range of ASCII characters. So this thing must be applied here, and anywhere that there is a usage of any normalizer, we need to make sure that we always use the NFC algorithm. So that is on there, and I don't want to solve this for you I want to leave the challenge as a fun activity so you can do it later. The other thing is, once these changes are applied, you're gonna go ahead and run make security test, and this time what you expect to see that all these security tests are passed. That is step number 1 or step number 2. The other thing we want to do is we want to go back, and given all those discussion we had about Unicode, we want to go back here and complete this security test, because what we're clearly missing here is that we only testing for a few examples of Unicode characters. So things such as Big Bird or these characters that you can see here and here. But this doesn't mean that we are safe or our security tests are complete. What we are interested is to find a way that you try to test for every combination of these Unicode characters. So that would be another challenge for you to have a look. Now I want to pretty much conclude the whole workshop here, and please go ahead and apply these things that we have discussed. And if you have any questions, you can head to discuss.secteam.com. You can directly ask your questions from us, and we will be more than happy to guide you through. Let me conclude this workshop with the references for a few things that we talk about and a few recap. So let's remember that let's just remember there is nothing such as a string in a sense of ASCII these days. Every time you see a string, think Unicode. So, and this is to do with all those characters that are allowed within the string data type. I think if we have this shift in our mindset, we will be more careful next time when we define something as a string, either in our front-end program or a back-end, and we always need to make sure that there is a normalization, there is a filtering process happening there. When you are dealing with identifier, our safest choice is to restrict the identifier to safe ASCII range and do not allow Unicode, and more importantly, case fault the identifier or that untrusted data that you have received as an identifier before doing any validation, any string matching. Or even what by a string matching, I am also referring to things like if you want to throw it inside a regex, make sure the data is already normalized before. And when it comes to the visual spoofing, one thing that I would like you to take away here is that you need to detect in your code 4 BD characters, confusable, or any other homoglyphs. And then later on warn the user that, hey, there is existence of such a thing in a code, what you want to do. And then finally, our references. So those, if you are curious to find out that what actually happened in those code snippet that I had for Java and Python, and there are quite plenty of them, this was based on a research paper that published in October 2021 and is known as a Trojan source code, which impact quite a lot of languages. We have example of Go, there's example of Rust. I would do encourage you to go and have a look at them. And a lot of the content that I had here was more like a simplified version of the 2 security reports from Unicode, known as a Unicode security consideration, which I do encourage you to have a look if you are interested. Well, that was all. And we will continue these workshops every first Tuesday of every month. And if you are interested, you can feel free to join. There are collection of lots of free courses in our learn.sectim.com platform, and you can use our discussion forum to ask us questions. Thank you.